And ladies and gentlemen, welcome once again to the Simpkins Physics Corner. Today it's projectile concepts. We're going to talk about X and Y independence when it comes to horizontal and vertical motion of a projectile. The thing we want to keep in mind today is that time is the same. You'll see what that means here in a second. We're going to look at some of the big concepts for projectiles, and then we're going to take a look at some quick projectile problems. Next lesson will be the more detailed one. So here we go, without a doubt. Dropping stuff, all right? If we drop stuff, then we know that it will accelerate with an acceleration due to gravity. So here's an elephant and a rock being dropped from the top of the building. Don't worry, the elephant was not harmed in making this film. The acceleration is always negative 9.8 meters per second squared, at least if you're close to the surface of the Earth. Now, we know that acceleration means that your velocity is changing. Acceleration is when velocity changes, all right? And so if the velocity is changing, in this case, if I start from a velocity of 0, because my initial velocity up here, my v initial y, if you will, was 0, the speed is going to increase by 9.8 meters per second every second. That's what 9.8 meters per second squared means, by the way. It means that for every second that passes, your speed changes by 9.8 meters per second squared. And then, of course, the displacement, though, increases exponentially. Now, that sounds fancy, but all that means is that when you're going slow, you're going to cover a little bit of distance, but as you continue to gain speed, you're going to cover more distance per time as time goes on. And if you were to graph these three things, you see your displacement graph, you would be starting from rest. Remember that the slope of a displacement graph tells us about the velocity. So that's 0 slope, 0 velocity, negative velocity, more negative velocity, more negative velocity, more negative velocity. And you notice this parabolic curve that comes from the quadratic or the exponential relationship between displacement and acceleration. For velocity, you would start from rest, so your velocity would be 0, and then it would increase in the negative direction in this example. And then your acceleration would be a steady 9.8 meters per second squared. So there's a quick little graph recap for you there as well. Let's look at the math for something that just falls straight down, pretty straightforward. How long does it take a golf ball, to fall from rest to for a distance of 9.8 meters? So the first thing you want to do is establish a coordinate system. A lot of people don't do this and they get really burned on all these types of problems. So if you want to fall a distance of 9.8, you got to decide where 0 is. So I'm going to make 0 the ground, and I'm going to make a positive up. Now, if that sounds absurd to you, it's not, because you need to be able to organize which way is up and where do you start. Because now that I make my list of knowns here, it's going to look a little something like this. The initial y, the place that I start, is 9.8 meters, and the final y is going to be 0 meters. This is your final y, this is your initial y. It says you fall from rest, so that means v initial y is equal to 0 meters per second. I'm just dropping it. The question is asking how long does it take for that to happen, so that's time. And the acceleration, since we're in free fall, is negative 9.8 meters per second squared. It's negative because I defined positive as up, and then of course we all know gravity is down. So when the question says how long, we need to find an equation with time. Now, I could use this one. The problem is I don't know time, and I also don't know the final velocity, how fast it's moving when it hits the ground. Okay. How about this next one? We look at all these things. I know where I started. I know where I finished. I know that I dropped it from rest, and so time is here and time is here. Now, it turns out that that is the correct equation. Why? Well, because the third equation doesn't have time. How are you going to solve over time if there's no t in the equation? Let's see how this plays out. Now, these are how the equations show up on your equation sheet. But remember, you can magically turn all the x's into y's or the y's into x's because kinematic equations work in any direction you want to do them. So we have y equals y initial plus vy initial t plus 1/2 ay t squared. Now, v initial y, it turns out, is really convenient for this problem because v initial y is equal to 0. What's 0 times anything? It's 0. So this whole term just goes away. Why? Because v initial y is 0. Let's fill in some stuff. We know that the final position is 0. We know that the initial position was 9.8. I should be putting meters here to practice good physics. Plus 1/2 negative 9.8 meters per second squared times t squared. And so it turns out to solve for t here, I could combine these two terms. That would be negative 4.9 t squared. I could set it equal to negative 9.8 meters. Why? Because I subtract it from both sides. And this problem actually turns out to be pretty simple. The next step here would be to divide both sides by negative 4.9, which of course would get us 2 over here. And if 2 is t squared, then you have to take the square root of both sides, and t would be equal to the square root of 2, which, if memory serves, is something like 1.44, but I'd like to get you the 100% right answer. So let's just see if my calculator will decide to wake up and work here, which would be fantastic. There it is. Square root of 2 is 1.41. Sure. Oh, sorry, I skipped ahead like 1,000 slides. My bad. All right, t is 1.41 seconds. Okay, so that's a little quick one as far as how the math would work out just for free fall. Free fall ones are easy because the v initial y is 0. Let's look at another one. What if I toss the ball up into the air? All right, same rules apply. If as soon as it leaves my hand, people are like, well, you pushed it up. Yeah, I did, but as soon as it leaves my hand, it's now a projectile. Okay, and projectile here is defined as an object thrown by the exertion of a force. It can also be defined as an object launched into space and allowed to move free under the influence of gravity and air resistance. Now, we're going to always ignore air resistance. Why? Because we don't have the math skills to handle it, and because oftentimes for a dense and small enough object, it's negligible. So our definition of projectile is something that flies through the air under the influence only of the force of gravity. Okay, so given that definition, let's go back here. Now that we've all talked about what a projectile is, let's see how that applies here. It's a projectile as soon as I toss it into the air. It goes up, comes back down. On the way up, right, the acceleration is down. So I have an initial upwards velocity, but every second that goes by, my velocity is decreasing. Why? Because there's an acceleration down. Velocity up, acceleration down. They're opposite. That means you lose speed. And so if we were to graph all of these, we would have a large positive velocity, and then be slowing down, slowing down, slowing down until it reaches the peak. At the top, important point of the day, at the top, your Vy, I could call it initial or final, I guess, your V up here is equal to 0. Why? Because if you are on your way up and then you're on your way down, at some point in the middle, you had to be doing nothing. You had to go from the positive to the negative. It would look like this on a graph. You would have a positive velocity. Your velocity would be decreasing steadily until you reach 0 velocity. This, by the way, is this point here at the apex. And then you would gain speed downward. Okay? Can anybody tell me what the slope of that graph would be? Oh, negative 9.8. Why? Because the slope of a velocity graph is the acceleration, and we're accelerating due to gravity. All right? So similar rules, just applied on the up and on the way back down context here. So let's look at one that's a little bit more challenging. If a stone is launched straight up by a slingshot, and it says how high above the ground would the stone rise, and how long does it take to hit the ground? Okay, so here we go. Now, we got to do our same thing. We have to establish our coordinate system. So we got to say, where's 0, what's up, all that kind of stuff. So I'm going to make up positive, and it says the stone is launched from 1.5 meters above the ground. It's thrown up into the air. So let's make a list of our knowns. The first one says, how high above the ground does the stone rise? So we can imply that that's asking for all the way up here at the apex, the highest point. We're going to call that y final. And we're going to call that, this one, y initial for this part of the problem. We also know that the v initial y is equal to 25.2 meters per second. That's right there in the problem. So if we pull this all together, we got y equals I'm not sure, y initial equals 1.5, acceleration equals negative 9.8 meters per second squared, because we defined up as positive, and we have v initial y is equal to 25.2. Now, this question says how high above, and if you look at these variables, sometimes what you don't know tells you more than what you do know. And what we don't know is time, all right? And so since we don't know time, this is the only equation we might even be able to use, because these have time in it, these have time in it. Those aren't going to be helpful. Let's go ahead and set this up. Vy squared equals Vy initial squared plus 2ay y minus y initial. Okay, oops, sorry. It loves to skip ahead after I write a big equation. Here's the thing, ladies and gentlemen. What do we know is the Vy. In other words, if I define the end of this problem right now as when it gets to the very top, what's the velocity? 0. That's right. So 0 squared equals 25.2 squared plus 2, 9.8, negative 9.8, I should say. And then y would be our unknown minus 1.5. Now, I'm going to wave my magic algebra wand and do a little bit of algebra here. So here we go. 25.2 squared is 635.04 plus, all right, and over here we got 9.8 times 2, which is going to be negative 19.6, and then times y minus 1.5. Now, a lot of folks will erroneously try to add these two together. You can't do that. All right? The second term, 19.6, is multiplied by that whole quantity, and it's kind of attached to it by multiplication, if you will. The correct next algebra step would be to subtract this quantity, 635.04 from both sides. Oh, I love when it does that. And so that would get us, I'll clean it up a little bit and write a little slower here, negative 635.04 equals negative 19.6 y minus 1.5. Okay, I've got to love it. The next step would be to divide both sides. by negative 19.6. And 635.04 divided by 19.6, 32.4 equals y minus 1.5. Add 1.5 to both sides, and we get our final answer here. How high above the ground does the ball go? It goes to a height of 33.9 meters. Now, I'm not going to do the rest of the next one because I have a few concepts to cover today. But when it says how long does it take to hit the ground, let's go back to our drawing here, and I'll use a different color. Maybe, if it'll let me. Yep, it will. Now the problem is this is the same. The v initial is the same. The y initial is the same. Now the y final is different. Now the y final equals 0. And the question is saying, how long does it take to do that? We need to solve for time. So let's consider our equations. This doesn't tell us anything about position. Not going to work. This one doesn't have time in it. And we need to solve for time, so that's not going to work. So which equation works? The second one. All right, you can see this, this quantity right here is going to be 0. This is going to be 1.5. This we know from the problem. T is unknown. A is known. T is unknown. Now here's the trick. I'm going to encourage you guys to go back to my YouTube channel and look at the 5-minute one where we did the free fall problem. I showed you. It says how to use your graphing calculator to solve for T. Go watch that video, and then you'll know how to solve for the time there. All right, let's talk a little bit more about projectiles. We defined what they are. But what if things get interesting? What if we're moving in both directions at the same time? We know already, we've established that in the vertical direction, you're always accelerating, and we also know that objects in motion stay in motion unless acted on by an unbalanced force. So this is why things accelerate vertically. Because if the force of gravity is the only thing pulling down on you, as you see in this diagram here, that's the reason why you accelerate in the vertical direction, because gravity is an unbalanced force. Okay. How about the horizontal direction? Look at this bowling ball. As soon as it leaves his hand, it doesn't experience any other forces in the direction up and down the lane. Now, sure, it's got some spinny stuff going on. We're not going to get into that now. But once the ball is rolled, there's no force down the lane, so the ball rolls at a constant speed unless acted on by an outside force, unless it hits the pin. What I'm showing you here is that in the horizontal direction, if I send something and I throw something through the air, all right, once it leaves my hand, there's no horizontal force on that object. All right, and so the horizontal direction, when we talk about projectiles, the horizontal direction is always a constant velocity. All right, the objects in motion stay in motion unless acted on by an unbalanced force. If there are no horizontal forces, there's no reason to accelerate. So if we put this together for projectiles, imagine this. Imagine I shoot something out of a cannon and it goes, pew! I'm sorry, my little drawy thing isn't working. And it goes like this. We know it's going to take a path that kind of looks like a parabola, like that. All right. What if we break that down into two pieces? Well, horizontally, once the cannon explosion happens, there's nothing pushing it to the right anymore. So what's it going to do? It's going to go at a constant velocity. An object in motion stays in motion in the direction it's going. So in the horizontal dimension, there's no other forces. It has no reason to accelerate. But in the vertical direction, it's always accelerating because the force of gravity is unbalanced. And so what we're illustrating here is you see how these guys are spaced evenly. That's because we have a constant velocity in the horizontal direction. These guys are gaining distance every second, or you're covering more distance every second because you're accelerating. And when you put them together, that's where you get this curvy path. So let me show you another illustration here. Take a look at these arrows as you see them. All right, in the x direction, velocity is constant through the entire flight. In the y direction, the acceleration is constant. You'll notice that the vector to the right has the same size for every little snapshot that you see, but the vector that's going down is gaining or is growing in size because we are speeding up as a result of that vertical acceleration. Here's the big idea: independent but simultaneous. See, if I ask you to time how long it takes this person to go up and come back down, and then I ask you how long does it take to go from the edge of the cliff here out to where he eventually lands, if you time both of those things, you would get the same answer. Why? Because you're moving up and down at the same time that you're moving out. You're moving in two dimensions. You're moving in x and y dimension. They're happening independently, but they're happening at the same time. They're independent but simultaneous. All right. So here's the big ideas for today. Horizontal motion is always constant because there's no unbalanced forces. Vertical motion is always accelerated because of that unbalanced force of gravity. And horizontal motion and vertical motions happen independently but simultaneous. My horizontal speed doesn't care how strong the gravity is, and my vertical motion doesn't care how hard I threw something. Right? Yes, they're going to have an impact on the overall flight of the projectile,
but the X and Y motions are independent and simultaneous.